so last time we talked about, we just did the theory behind the fundamental theorem of calculus, and last time we talked about how we solved the fundamental theorem of calculus. And so today we're going to practice doing a bunch of examples of solving. So remember, the fundamental theorem of calculus is how we solve the definite integral. Remember, the definite integral is that infinite sum of my function from one point to the other, so long as it's continuous. All right, and it can be positive or negative. All right, it's the accumulation of the function values. All right, so let's do, the first example is going to be one where it comes out completely positive, and so it does end up being the area. All right, so I'm going to integrate from 0 to 3 my 6x to the second, not cubed, plus 10x, or 10 with respect to x. All right, so the fundamental theorem of calculus, when we're solving these, remember, math is a language. We use our own notation and terminology, and they have meaning and correctness. Just like when you're in an English class and you have correct punctuation, citations are correctly done. Well, this is setting this up with the correct notation. All right, so to solve this, the first thing you do is write down any antiderivative. It can be any of them. There are infinitely many antiderivatives you could write down. We'll usually pick the one with a constant 0, all right, or there isn't a constant. And so the general antiderivative is 6x to the third divided by 3 plus 10x, but I'm not done yet, right? The notation is, well, I've only taken care of the integration part. I haven't taken care of the accumulation part yet, the 0 and the 3. And so you can either do a straight line, or I sometimes like to use a bracket because it reminds me I'm going to take 0 and 3 and plug them in. And this is the way we write it, right? This is the math symbols and the correct notation. We write the general antiderivative, and then at the end of it, you draw either a line, or like I said, I like a bracket, and then my lower value and my upper value. And then my next step is to take my upper value, plug it in my general antiderivative, and then subtract, plugging the lower value into my general antiderivative. That's the notation we're looking for. That's the fundamental theorem of calculus rule and notation. All right, and then you actually do it. So I'm going to plug in my 3 into this general antiderivative, write my value in, plug my 0. Well, 0 is easy. When I plug 0 in, this 0's out, that 0's out, so I'm 0. 3 in, so it'll be 6, 3 cubed divided by 3, plus 10 times 3, and that simplifies to 84. All right, so the answer is 84. All right, and to put that in context with a picture, all right, so that's what that integral equals. If we draw this function, so if we graph the given function, all right, so the given function was 6x squared plus 10. All right, if you graph that on your calculator, it's a parabola that opens up. You'd have to make your window a little bigger because, again, it's going to start at 10. All right, it's a parabola that's opening up. We integrated from 0 to 3. All right, my function's completely positive everywhere. And so what we did is, well, we accumulated the function values between 0 and 3. All right, that's what it is. All right, and when we accumulate them, that finds my area under my function f of x over 0 to 3 is equal to that integration of the function, which we found was 84. All right, so that area is 84. All right, this cumulative sum of my function values between 0 and 3 is 84. All right, I'm going to do another example. All right, so my second example, integrating from negative 4 to 1 of my function 4x cubed minus 6x plus 5 with respect to x. And I'm going to go ahead and do the simplifying in my head. Right, 4 is going to come along. I'm going to take my power, add 1 to it, so it'll become 4. Divide by 4, so the 4's cancel. Just leaves me with x to the 4th. 6x, so it's going to be 6x squared divided by 2, so that simplifies to 3x squared, and then I get a 5x. Not done yet, so again, you either put a straight line, or I like brackets. Still have to take care of my upper and my lower values. I take care of them by plugging my upper value in, subtract, plug the lower value in. Again, that's the notation we want to see. And then you do it. You take your 1 and you plug it in. You take your negative 4 and you plug it in. You're plugging it into your general antiderivative. That's why it's capital F of x. And when I plug in my 1, well, that's going to come out 1 minus 3 plus 5. come out 2. Oh no, sorry, 1 minus 3 minus 5 is going to come out 3. Forgot my 1. Alright, then I plug in -4, plug -4 into that. So -4, don't forget it's -4, put parentheses around it. So -4 to the 4th is going to come out positive, -4 squared is going to come out positive. And so it comes out to 188, but now we're subtracting. Alright, so the answer is -185. And so that means this function either has all or some of its area below the x-axis, right? Because again, this would be where area above, area below, right? Is the difference between the area above and the area below. So I'm going to, again, show you the graph of this function. Alright, so if I graph the given function, not the antiderivative, I graph the given function, the 4x cubed minus 6x plus 5. Alright, the shape comes out Alright, so there's the graph of that function, and we're integrating it from -4 to +1. Alright, so -4 to +1. And so we'd accumulate the area here from -4 to that point. Alright, so that's negative. And then we'd accumulate the area here up to my 1. So there is some positive area. Alright, so it's not area. What it is, it's the difference of area. So what this means, alright, this integration from -4 to 1 of my function 4x cubed minus 6x plus 5 equals -185. And so that means there's more area below than area above. Alright, there's exactly 185 units more area below, right, when I take the difference, right, because it's area above minus area below equals -185. Alright, so when I take the area below and subtract it from the area above, I'm left with a -185. So there's that much more area down here than there is up there. Alright, that's what again, it's accumulating. Alright, so it's accumulating all these negative y values and all these positive y values. When it's done accumulating them all, that's the amount that I'm left with. Alright, so I'm going to do a few more examples. These I'm not going to graph, I'm just going to find. Alright, so the next example is a simple 0 to 4 of my 10e to the 2x dx. So this should come out a fairly large number, right? It's an exponential function. It would be completely positive, right, if I graphed it. So this is the area under my function from 0 to 4 if you graphed it. I'm going to leave off the graphing this time. I'm just going to find it. Alright, so first step, find my general antiderivative. Well, remember, it's the original 10 at e to the 2x, but I'm not done yet. I divide by that k out front, that 2. And then I still have to plug in 0 and 4. If you want to simplify before you go to plug in, you can. Alright, so we're going to plug 4 into that expression and subtract plugging in 0 into the general antiderivative. Alright, so it's going to be 5e to the 2 times 4 minus 5e to the 2 times 0, which comes out 5e to the 8 minus 5. Alright, and then plug that in. It says exactly what it equals, 5e to the 8 minus 5. And you can plug that into the calculator to get the approximate 14,899.79 if I round a couple decimal places, which would represent area. Like I said, it should be a fairly big number because exponential functions are fairly large. Alright, let's do another example. Alright, 1e squared. E squared's a number, it's just an irrational number. Alright, so I'm going to integrate from 1 to e squared of the function 3 over x plus 2. And so remember, 3 over x is that special case. When I find my general antiderivative, 3 is just going to come along. And when 3 comes along, I was left with 1 over x. Well, the antiderivative of 1 over x was the natural log, and we always do absolute value. Natural log of x. Alright, so there's the antiderivative of 3 divided by x, and then 2x for 2, integrating from 1 to e squared. And so, again, show that, the general antiderivative, and then I haven't plugged my numbers in, and then you plug them on. f of e squared minus f to the 1. Alright, and that simplifies. Alright, so it simplifies exactly to 4 minus 2, but you could use the calculator in a point and find out that it's 18.78 if I round a couple decimal places. Alright, let's do one more example. Alright, so the answer to that was 18.78. Alright, so one more example, and then we'll stop there, and then the next set of notes, I'm going to show you how you can solve this a couple of different ways on your calculator. Alright, so our last example. Alright, so this one I have to do a little work for, right? We don't have a product rule, and we're not going to. We don't have a quotient rule, alright? So if it's a quotient or a product, either we can manipulate it and change it, or if it's a quotient, it's our special case, which is our logarithm. Alright, this one I want to get rid of the multiplication by distributing, so that's my first step. So I haven't done anything with the integration, so it stays. All I'm doing is rewriting this so I can find my general antiderivative. Alright, so to distribute it, I get 6x to the 4th, 2x to the first, right? I add my exponents, so 3 plus a negative 2 comes out positive 1. Alright, now I'm ready to find my general antiderivative. Alright, so 6x to the 5th divided by 5. Antiderivative of 2x is x squared. Alright, still haven't taken care of my upper and lower values yet, so I write them, I bring them along. Alright, now I'm ready to plug in my 10 and my negative 5 into my general antiderivative. Alright, so I plug those values in, I find them, so this is all the work we want to see. So when we say we want to solve the general antiderivative by hand, these are the steps we're looking for. We're looking for that you have the general antiderivative, right, which takes care of the integral part, which means I don't have an integral anymore, so there should not be any integral now. But I haven't taken care of my upper and lower values yet, so we put it at the end as either a straight line or, like I said, I could use a bracket. Leave my them. Show that what I'm doing is then plugging those into my capital f of x, which stands for my antiderivative, so I'm plugging them here. Right, and then you actually give the values when you plug them in there. Alright, these come out pretty big. When I plug 10 in to that antiderivative, we get 20100, and when I plug in negative 5, I get negative 3725. Alright, which remember, a negative minus a negative really means I'm going to add those. And so my final answer comes out 123875. Alright, and there is my general antiderivative, or my definite integral solved by hand. Alright, so like I said, I will ask you to solve these by hand on tests and homework, and when I say solve by hand using the fundamental theorem of calculus with correct notation, this is what we're asking for. Alright, so solve it like this, using the correct notation, just like if you were in an English class, and they ask you to cite something using the correct citation notation, same thing. Alright, we'll stop there. The next set of notes are going to be, well, I'm going to show you how to do this using your calculator. Alright, there is a way to do this on your TI 83s, 84s. Alright, and I'm going to walk you through that in the next set of notes. Alright, so I'm stopping there.